Good evening, everyone. So today, welcome to the third tutorial session on rocket propulsion. Today, we will be dealing with the rocket nozzles, and the isentropic flows. So, before jumping on to the tutorial part, I would like to know if you have any questions regarding the assignments. So, we can have a discussion. So if you have any doubts on the assignment problems, we can have a discussion now. Yeah, Pranjal, please go ahead. Okay, can you please tell me the problem? Uh, okay, so can you please tell me the complete problem? So the structural, huh, hmm. Oh, is it? So probably I'll take up this issue to the assignment. Uh, so I am here to clear your doubts actually. So for taking up uh, the technical part, I'll inform the NPTEL authority. Okay, so the correct answer, what you're getting is the same, but the marks has not been given to you. Okay, okay, okay. We'll try to uh, uh, resolve the issue. So I'll escalate this issue to the NPTEL people. So they will take care of this. Yeah. So okay. So anybody else is having the doubt? Before jumping onto the tutorial session, I would like to take up your questions. Yeah. Right now it is for week 3. So in this, we will be dealing with the rocket nozzles, uh, and I'll be trying to do the assignment problems which you will be having in the assignments. Some sample problems I'll do so that you can have a good grasp on the assignment problems. Week 3, yes. So I'll be dealing with the rocket nozzles today. Yeah. Any other doubt? Okay. So uh, I'll start the tutorial session. So I'll just brief it out the relations which were taught in the class, and then I'll take up the question sample problem. So I hope everyone is clear with this equation. They know what this equation tells, right? This is area Mach number relation. Basically, it tells if you have a area ratio, say this is 80 here denotes the throat area. Uh, this is your say AE. If you have this area ratio, then uh, and if the Mach number here is 1, so what is the Mach number at this point? So with this, you can calculate this Mach number at the inlet, or this is also valid for the exit area. say if you have a rocket nozzle, you have a exit area and the throat area, and it is given the Mach number at the throat is 1, which means the nozzle is choked. Okay, so so what Mach number you can expect with this? So if you see this plot, you can see for a given area ratio, um for a given area ratio, you have two solutions, one at this and one at this location. This is known as uh, subsonic solution, and this is supersonic solution. So basically, what this equation is telling you here is, if you have a so say if you have a nozzle that is and the Mach number is choked. This is AE, this is AT, and if AE by AT is given, so depending on the direction of the flow, you can have different uh, Mach numbers. So with this relation, you can calculate what is the Mach number at this point, given your Mach number is area here is choked. Okay, so okay, uh, right. So coming on to the other relation, this is the isentropic flow relation. So basically, it tells if you have the inlet Mach number and your the change in area is given to you. So what will be the change in the velocity of the flow? So if you have a converging section, so for this case, dA by A is negative, right? Because the area is decreasing from section 1 to section 2. Okay, so dA by A is negative, and if the Mach number is subsonic means Mach number is less than 1, right? So this term dA by A is negative, then 1 minus m square term is also negative for Mach number less than 1. So dV by V will be, anybody? This has to be positive, right? Which means if you have a converging section, if you have a converging section and the Mach number is subsonic at this section, so you will see that the velocity will increase along the flow. Okay, will be greater than zero. I hope this point is clear to everyone. Yes, right, right. Yeah, so what here I mean is, okay, okay. So dA by A 1 minus m square dV by V, right? So if you have a converging section, so along the flow your area is decreasing. So which means if the area is reducing as you go along the flow, right? So dA by A for this type of geometry is less than 0, right? Because so this is A1, this is A2. A2 minus A1 by A1 is negative, right? Is less than 0 because A2 is less than A1. Okay, so this part is negative. And for a subsonic flow, if Mach number is less than 1, this also is negative, right? Which in turn says that dV by V is positive, which means if you have a velocity V1 and at the exit the velocity is V2, then dV by V is greater than 0, which means V2 is greater than V1, right? So this is what we see when we have nozzles. If you have a hose and you have a nozzle and the area is decreasing, and if so the velocity at the exit will increase. This is the consequence of this equation. Okay, so uh, okay, here we can write that velocity is increasing, right? Then let us look at the other case. Let us look for the diffuser. Huh. Yes. Hmm. Yes. Right. So, minus AdP. Which part? Huh. Huh. This part, right? So momentum equation, if you take along this section, okay. So you have pressure P1 plus rho 1. Okay, just it will be just a Bernoulli equation, right? Then you can express if the flow is incompressible, you can express your um, uh, rho A1 V1, you can express into the continuity equation. So P1 plus rho 1. This is just if we assume V1, P2 plus rho 2. Here you can get uh, okay. With this relation, you can calculate this A1 by A2 into V1, right? This is what you mean? Or hmm. Okay, so it will be dP is equal to I guess it will be uh, rho dV, right? It's minus. Okay, right. That's what I have written, right? dP is equal to minus. Okay, this is just the Euler equation, right? Which you derive. So this is when this area gets cancelled out, okay, and you have uh, yeah, please. Right. So let us calculate. Let us derive this equation. Okay. Uh, so if you have some section, okay, this is some arbitrary section, and I'm calculating So if I assume a controls surface around this, okay, now we have to do a force balance. Okay, so this is if this is P and this is P plus dP, uh, the velocity is V. This is V plus dV. Okay, so what we are saying here is, and if the area is A, okay, so what will be the what will be the pressure force on this surface? It will be P A, okay, and then minus, because this surface will be facing this uh, okay, minus P plus dP into A will be equal to uh, m dot uh, okay, it will be just equal to the momentum that is being changed, right? So dV minus m dot V. So this is m dot dV. This is uh, minus dP into A. This is what you are getting, right? Okay, okay. You can understood. You can think in this way. Uh, the pressure, the okay, the pressure that is felt on the surface will be in this direction, whereas okay, what we are saying is here is the pressure is always normal to the surface, right? So this is P plus dP, and this is the velocity is in this direction. Okay, then this is towards a negative x-axis, right? If I consider the axis here, okay, this is negative x-axis. Okay, then that's a negative here I have taken, and this is positive. Okay, then okay, so because the pressure is normal to the surface, that's why the direction has because of the direction thing, we have taken it negative. Is it? Is it? Hmm, hmm. Right. So okay, so when you see the derivation, so this will be dx, and so what we usually say here is, and this is some a plus dA, okay, or a minus dA you can take, okay, a minus dA. So this the change in area is okay. This is for this surface I'm talking about. I'm talking about the exit surface. So this, if I assume that there's a small theta at this section, so sine theta is equal to, so this is say there is some, this is some dx, small length dx, not dx, x I have used as a, okay, dx, then this will be dx by uh, okay, this is okay, this will be some, this a minus dA by 2 divided by ds, right? So what we assume here is the since we are talking about two sections that are very close to each other, the ds is very small. Okay, So with this, we assume that this. Okay, 1 minute. Okay. No, no. So okay, if I write this equation, if okay, for this condition, what we have to do is we have to consider the pressure force on this surface also. Then okay. So if we assume that this is P plus dP by 2, some mean pressure that is being exerted on the surface. Okay, B by 2. So if you take the component of these 2 points, okay, this the y component will cancel out from the bottom surface, and you will be having second order term, some dP and dA by 2, something like you will get like this. Okay, so this thing you can, yeah, yes, we are using Taylor series for this. So when you're writing this thing, we're just using a Taylor series for this. Okay. All right. So if you have, yeah, so if will have a second order term, okay, then that can be neglected. Right. Exactly. Yes. Yes. Okay. Yeah. Anything else? Any other doubt? Okay. So, okay. So, right. So coming on to the choke mass flow rate. So basically what it is telling you here is if you have a nozzle and what we start to do is we start to increase the pressure given my back pressure is constant. Okay. So depending on the, yeah, please, please, yes, yes, right. So okay, maybe let us try. What I will try to do is I'll try to do the formal derivation of these two things. Okay. The both whatever you have asked. Okay. So maybe you'll get a more clarity on this. Then. Okay. So okay. So let us. Um, okay. Let me see where were we. Okay. Give me a minute. So let me recall the things. Uh, because mm, okay. Okay. Let us start with your first problem. That is the uh, relation what you were asking, right? So let us okay, so let us consider a control volume. Okay, I hope control volume and control surface is clear to you all. Okay, so with this you have we have a control volume, and we have, and it is given that the area of this part is A, and this part is dA. Okay. uh, uh, dA, basically this and this complete these two surfaces, dA. Okay, or this can be written as dA by 2 and dA by 2. So this complete area will be A plus dA. Now, uh, At this surface, we have pressure force, say P, and this theta. Let us assume that this is small theta, and this at this surface we have P plus dP. Okay, so let us try to now, yeah, and we assume that at this surface we have P plus dP by 2, some average pressure. And so now what will be the area of this surface? So if it is dA by 2, so it will be dA by 2 uh, sine theta, right? Because sine theta is dA by 2, uh, minute, yeah, dA by 2 into this length ds. Okay, so if you take this area, and if I assume that this is a unit width, okay, for so this will be dA by 2 sine theta. So now let us calculate let us use the momentum equation, and which will be equal to the sum of external force is equal to m dot v uh, out minus m dot v coming in. Okay, and if you assume that this is v and this is at this surface, it is v plus dv. Okay, so the net resultant force in x direction is um will be PA minus P plus dP by 2 dA by sine theta. So this will be the pressure in this direction, and you have to take a component of this, right? 1 minute. So this will be so probably, yeah. So okay, then if dA, and it will be sine theta uh, will be equal to m dot v plus dv minus m dot v. Okay, so if you take this PA minus P, this sine theta will go off. Okay, let me make the angles right. So this is theta, this is theta. Okay, then so the component will be in this direction, no? Okay, so this is P plus dP by 2 dA by sine theta to sine theta. So this is okay. We were having half, right? Half. So this is from the bottom surface. Similarly, we'll be having from the top surface also, right? So so we can multiply it with 2. Okay. So this 2 go off, sine theta will go off, and you will have PA minus P into dA. Uh, okay. Okay. This is 1 minute. This is uh 1 minute. So this is from the side walls, right? This contribution is from the side walls. This is from the left wall, and we'll also have a term from the uh, right wall, A plus dA. I hope you all are there with me. So okay, this is P plus dP, A plus dA is equal to m dot dV. So right. So we have P into dA plus dP dA by minus dP dA plus minus PA minus uh, uh, PdA. Then you will be having a term for second order term. Then I hope I have missed P into dP, right? These all terms will be there. So you can cancel the terms. 1 minute. So this will be okay. This will be in this direction. Probably this is in positive. 1 minute. This is in positive direction. Sorry for this is in positive direction. No? So this is fine, right? Let us cancel the terms. This thing is gone. Then this is the second order term. This you can neglect, right? Similarly for this is a second order term. Okay. Uh, right. And what else? So this is gone. So only the term that is left here is A into dP, uh, and it will be negative, right? Because it was yeah negative because it is yeah minus dP into m dot dV. I hope this answers your question. Why we are having this minus sign, right? And why not we have not? Huh? Okay. So let me answer your second doubt. The speed of sound, right? Okay. So okay. Yes. Um, okay. So let us think about a tube. We have a piston cylinder arrangement. Okay. We have a piston, and what we do is we give a small impulse to this piston, such that the molecules at this point are pushed little to the right. Okay, they are pushed little to the right, which will create a small pressure wave. Okay, that we usually call it as a sound wave, right? To now so if you have to balance your mass momentum and energy, so you can do it in either way. You can either choose a lab fixed coordinate frame, or it is always better to choose a frame that is so that your wave is stationary to you. Okay, this from lab frame to this sound uh, to to the moving frame. Okay, if I assume the sound is traveling at a constant velocity, so we can have a coordinate transformation that is known as Galilean transformation. Okay, so what we do is instead of looking from this location that the sound is moving ahead, what we do is we sit on the sound wave itself. Okay. And what we do is we see what properties are coming in, what properties are going out. Okay. So, okay. So then what we do in the derivation, I think what we do is we assume a control volume. Okay. Then probably this is so Okay, then what we do is if we assume that this is moving with velocity a, okay, and we have the the gases that are moving with velocity v, so we can have a coordinate transformation such that you will feel that the velocity the the particles ahead of this is coming with velocity a and they are leaving with a velocity of a plus dv. Okay, related to each other. So this is how we do this Galilean transformation. So probably, I think if you take a subject, take a course on gas dynamics, you will find this thing. We usually do it for shock waves also. This Galilean transformation. Okay. So, anyways, so I think this answers your doubt, right? To so let us move to the nozzle part. So, okay, right. So we were on this, right? So if we ha now we said that if you have a converging nozzle and if the Mach number is less than one, the the flow will accelerate. Whereas a section, if we have a section which is diverging, and if we have a subsonic flow, so with this equation, what can we tell about the velocity? Anybody? Right? Because decrease exactly. So because it is so now what is dA by A for a diverging section? Positive. For subsonic, it is negative. Therefore, the dV by V will be negative. Okay, which means the velocity will decrease, right? So let us look for a supersonic flow. Okay, for a supersonic flow, if the area is decreasing, so this will be negative. For supersonic flow, this also will be a negative quantity, right? So this will be okay. 1 minute. So mm, this is negative. This is negative. So this will be positive. Okay. So greater than one. Am I making a mistake? Mach number greater than one. Converging section. It should decrease now. Uh, this is negative. For okay. Uh, hmm, okay. I feel 1 minute. Can you please check if it is this equation is correct? I feel it is it should be m square minus one. Can you please check somebody? Uh, 1 minute. It should be uh, yeah. 1 minute. So let me check this equation once. This is uh, hmm? It should be one. It should be negative, no? Yeah, that's what. So there will be a negative here, no? In this equation, there will be a negative, right? Okay. So, then, okay, then it will be this quantity will be positive. Okay, sorry. So negative, this will be negative. Uh, okay. So for a diverging section, for a converging section, if you have a supersonic flow, the flow will deaccelerate, right? So can somebody tell this where these type of converging sections are used to deaccelerate the flow if we have a supersonic flow? So uh, is this used somewhere? We have a supersonic flow and we want to decrease the velocity. Okay, so what I'm saying here is we have a converging section, and we have a supersonic flow, and our area is decreasing, right? So, the if the velocity is v1, so what we are saying is velocity 2 will be less than velocity 1, right? So, is this condition used somewhere? Okay, so let me answer this. Yeah, 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 exactly. So in a ramjet and scramjet engine, so what we want is we want to decrease the velocity. That is, so if we have a scramjet engine or ramjet engine like this. So right. So what we want is the flow usually comes at a supersonic flow, and we want to decrease the velocity so that we can have a we can sustain combustion at this point. Okay. In order to do that, we have to decrease the velocity. For which we what we usually do is we have a converging section, which reduces this velocity. Okay, so these are used in inlet of ramjet and scramjet engines. Okay, and similarly, if we have a diverging section and if the Mach number is greater than 1, so what we can expect is the velocity will increase, right? V2 will be greater than V1 because dA by A negative 1 by 1 minus m square is equal to dV by V. So diverging section, this is positive, this is this is negative, and again this is negative, this sign. So dV by V will be positive. Okay, so if we have a diverging section and if the Mach number is greater than 1, so we will have the velocity will increase. Okay, so this do you know where this principle is used? Any idea? Okay, there are two places where they are used. Somebody wants to answer this? Satish, right? Yeah, exactly. So in the CD nozzle, the the after the throat expansion part, this principle is used. This principle is used where we uh, used for accelerating the flow, right? Another thing is we also use it for a ramjet engine. In the nozzle part, after the combustion, the flow is supersonic. Okay, and if we want to accelerate this flow, we do not want a converging type of nozzle. We probably use a diverging nozzles in this type of flows. So these uh, these are used in scramjet nozzles as well as in the CD nozzle itself. Okay, so okay, so let us try to. I hope this graph is clear to everyone. Uh, do do you have any doubts on this? Maybe I'll repeat this part. I hope everyone has seen the lecture on this. Okay, so basically what we are saying here is, okay, so let us consider a case in which we will be maintaining a certain pressure, say say P naught, okay, and we have a CD nozzle, okay. So what here we are doing is we are trying to we what we will do is we'll decrease the back pressure. We have a vacuum chamber, some vacuum thing where we can decrease the pressure, and we want to monitor what is the pressure at each location along the nozzle length. Okay, so I want to do experiment where I want to plot the pressure versus length of the nozzle. Okay, this is the length of the nozzle. This is the x-axis where I want to measure the pressure, uh, and what we will do is we'll decrease the back pressure. Okay, so uh, when the exit pressure is equal to the inlet pressure, do you feel that the flow will take place? Uh, no. Why do you think so? No. Uh, so the pressure at the exit and the inlet are same, right? So do you th feel that the flow will take place if the pressure difference is not there? Huh? Uh, no, I'm just asking you that if what we are doing here is if the pressure are same at the exit and the inlet, do you feel the flow will take place? Yeah, pressure difference has to be there to have a flow, right? So if the flow is not there, so at every point the pressure will remain same, right? Right? So this is what the first. Okay, this is what our case first will look like. There will be no flow and the pressure will be same at every location, right? So then what we will do here is we'll try to reduce the back pressure now. Okay. So what will happen? The flow will take place since this part is uh, converging in nature, right? This part is converging. The velocity here will increase, right? And the pressure will decrease. So, so if I mark this place as a throat, this is the throat area, throat section. If I mark this place as a throat, then the uh, the the pressure will decrease, and again, as we there's a there is a diverging section. The flow will again deaccelerate, and the pressure will increase, right? And it will be equal to some pressure what which we have done. Now what we will do is we'll try to decrease the pressure again. Okay. So what will happen? The velocity will further increase, and the we'll have something like this. So a condition will come where the the velocity at the throat will be equal to the speed of sound. Okay. So at this point, when the Mach number is 1, the nozzle will be choked. Okay. So with this, we can either have a dive. So all right, then what will happen? This will again be a subsonic flow at the exit. But if you further decrease the pressure, what will happen? The flow will further accelerate. But what will happen? A shock will form into the nozzle. Okay, and this shock will form, and it will then across this shock, the pressure difference will be there, and you will have uh, a shock that is sitting inside the nozzle. Then if you further decrease the pressure, what will happen? Uh, what will happen? The shock will try to move toward the exit. Okay, and at a certain point, what will happen? The shock will be just at the exit of the nozzle. Okay, so this is shown in this experimental image. So this is what is happening. So if you decrease the pressure, so the shock will be residing at the nozzle exit. So this is the shock. So this is the Schlieren image. Schlieren basically what it is a experimental technique to capture these shocks. Okay, and here you can see the shock that is sitting at the exit. Okay, then if you further decrease, what will happen? What will happen? Uh, okay, so what will happen? These Okay, at point 0.6, okay. Then from at point 0.5, the shock is at the exit of the nozzle. From point 0.5 to point 0.4, the shock will become an oblique shock. Okay, and uh, as you further decrease the shock angle, so if this is theta, the shock angle will reduce, and at a certain pressure, the shock angle will become zero, and this is known as at this point, this corresponds to the design condition, that is the supersonic. You will get fully expanded flow. Okay, so at point 4, you will have a fully expanded flow where you do not have a shock. Now, if you further increase your decrease your pressure, what will happen? You will have a expansion fan at this point. Okay, you will have expansion fan, and you will have something. You have uh, uh, shock structure like this. Okay, so yeah, you have the expansion fan. I hope th this part Professor Ramamurthy has taken up. So so these are the images which I wanted to show. So these are the expansion fan, and again you see the shock structure at this point, right? So this condition is known as uh, right. So yeah. So this is 1 minute. So this is known as uh, overexpanded nozzle, and this is known as under expansion. Okay. So I have series of questions for you all. So this is some fighter jet, and I want to know by looking at the rocket plume. So can you tell me which type of flow is this? Either it is overexpanded or underexpanded. Can you tell? So probably it is a under expanded flow because as you can see in an under expanded flow you have so shock system something like this, right? So and also in Professor Ramamurthy's lecture he has talked about this shock diamonds, right? You have a region of hot flow, you have a region of a relatively cold flow. So this is here you can see the region of hot flows. The intensity is higher, right? So this is a under expanded nozzle. Okay. So okay. So can you tell me? So these are the uh, images for SpaceX launch, and I would like to know whether the rocket plume is under expanded, over expanded, or it is uh, it is at a design point. So can you anybody can suggest this thing? Okay, so here you can see the the nozzle plume is probably in a completely parallel direction, right? Parallel to the rocket. Okay, this something looks like a design point where you have a flow that is going parallel to the nozzle. Some yeah, optimum condition. Okay, so this is something like a optimum condition. So when this rocket goes to a very high altitude, we usually see a rocket plume something like this. So can somebody suggest why it is happening? So, okay, whether it is a overexpanded, underexpanded, or yeah, design point. Yeah, this is a underexpanded nozzle, right? Uh, Coming on to this, so can you suggest which type of no which uh this is Merlin engine from SpaceX again. So can somebody tell which type of configuration is this? Like under expanded, over expanded, or design point? It is actually it is over expanded because you can see the rocket plume is being pushed inward, which states that the pressure outside is greater than the okay PB is greater than P exit. Okay, which is trying to push the the flow inward. Okay, as you can see in this plot, if the okay, so if okay, in this condition, uh, 1 minute. So in this condition, 1 minute. So this is right. Huh. Okay. So in this condition, the P exit and P back. So the P exit is less than P back. Okay. At this, P exit is equal to P back, and this is P exit is greater than P back, right? So in this condition, what is happening? The okay. Probably I think 1 minute. Yeah, it is again. It is over expanded, only. Under expanded. Sorry, under expanded. It is under expanded nozzle. Okay. So okay. So coming on to the flow separation. So as you can see, so so you might have talked about this, learn about this divergence loss, right? So can somebody tell what is a divergence loss? Hmm? So probably what is happening? So if you have a conical nozzle and if the flow is going in a different angle, so what will happen? A component of the flow is lost in the other direction, and you will not get the optimum thrust. So this is what you see in this conical nozzle. Also, what happens if the flow angle is greater than a certain degrees? What will happen? You will see something. You'll see a flow separation, something like this. So these are known as so this is the flow separation points. So okay. So with this, I have summarized all the important equations uh, in this uh, uh, with this. So this is the choked mass flow rate, and this is the equation for the C star. Then we have a thrust equation, uh, and this is CF efficiency, C star efficiency, and the ISP. Okay, so let us try to do a small sample problem. So, okay, the problem is as follows. We have to design a rocket. Huh? Hello? Right. Now it is clear. Okay. So a rocket nozzle is to be designed. A rocket is to be designed to produce 5 kilonewtons of thrust. Okay. So this is given at sea level condition. So sea level condition, it means the P exit is given. So it will be 101,325 pascals. Okay. Now the pressure in the combustion chamber is 7 megapascal. So this is telling you P naught, right? So with this information, it is telling you P naught is 7 megapascal, and the temperature is 2800 Kelvin. T naught is okay. If the working fluid is assumed to be a perfect gas with the properties of air at a room temperature, so properties, what all properties do we require when we talk about the propellants, the gases? So this is gamma, right? 1.4, and R has to be taken as 287 joule per kg Kelvin. Okay. So so the first part is we have to calculate what is the specific impulse for the rocket. So um, how do we get that? Any idea? Any idea? Okay. So let us assume that the okay. So first part is specific impulse. Okay, what is specific impulse? Uh, Impulse by mass flow rate, or it can be so this is your impulse, right? Thrust by dt over some burnout time divided by mass of the propellant, right? Is it correct? Uh, but we also so in we can specify in either ways, either in so the most common unit is in seconds. So what we usually do is we divide by g. So what we say is the force that we get uh, for a given weight of the propellant. Okay, this is we can either have a mass or we can also have in terms of weight. Okay, so the thrust is given by m dot propellant v exit plus p exit minus pa into a exit, right? If I assume that it is, if I assume that it is a uh, fully expanded nozzle, which means at optimum condition, then P exit will be equal to the PA, right? So we have m dot P into VE, right? Now 0 to TB m dot V exit TT by mass of the propellant into G, right? I hope this is clear to everyone. This is visible, right? Okay. So what we do is, if I assume that V is constant and TB m dot propellant dt by mass of the propellant. So if a rocket is there, if you have a rocket and you have certain propellant, that is mass of the propellant, if you integrate this quantity, this should be equal to the mass of the propellant, right? If we have a complete burnout, right? Is it clear to everyone? So this will be MPVE by MP dot G. This is just V by G, which is equal to ISP. Uh, um, this is clear, right? This VE is just a exhaust velocity. So where MP is the mass flow rate through the nozzle. Okay, if you integrate over a time, so this will be equal to the mass of the propellant itself, right? What we are carrying. Huh. So we have this. Now we want to know what is the velocity at the exit. So we have a relation that 2 Cp T naught 1 minus P exit by P naught gamma by minus 1 by gamma, right? You have this relation. Okay. So or you might have seen in this way. This equation you might have seen in this gamma R gamma minus 1 molecular weight T naught 1 minus P exit by P naught gamma minus 1 by gamma, right? V exit. So this equation you might have seen, right? So for since in the problem it is okay, this is RU. This is universal mass constant, universal gas constant. Okay. So we probably will use this relation. So this is 2 Cp is for since in the problem it is given, we can take the properties as air. So Cp is 1005 for air, and this temperature T naught it is given as 2800 Kelvin. Okay, then right. So we have 1 minus P exit is equal to the atmospheric pressure, and P naught, that is a chamber pressure is given as 10 to the power 6. You have 0.4 by 1.4. Okay, this is V exit. So this is 1987.4367 meters per second. Okay, now the specific impulse will be V E by G, which is equal to 1987.4367 by 9.81, which will be equal to 202.5929. Okay, so seconds. I hope this part is clear to everyone. So what here we are saying is we have a rocket which is having 7 megapascals of pressure inside and 2800 Kelvin. And we have a nozzle that expands to the atmosphere, that expands through the atmosphere, and we want to know what is the ISP for this rocket. Okay, so the ISP, how we have calculated is by the definition itself. So the ISP is equal to the thrust, the O integrated over time divided by the weight of the propellant that is being used. If we assume that the velocity is constant over time, we can take the integral, the V outside the integral, and then uh, this m dot p over the time, which is it is equal to the mass of the propellant itself. We have this relation. Then the only thing was we wanted to calculate what is the V exit. Okay, so V exit we have calculated using uh, the this relation which comes from the energy balance, and with this we have calculated what is the ISP for this rocket. So any doubts on this till this part? Any doubts on this? Okay. Next thing is we have asked what is the choke mass flow rate. How will you calculate this? Okay. Come again. So how will you calculate the choke mass flow rate? Somebody was saying, right? Something. Ah, Satish, you were saying something? Okay. Right. So, but for this, do you know what is the throat area? I think in the problem it is not given, right? In fact, we are required to ask what is the throat diameter. So by looking at this, can you tell something, some other equation we can use? I hope this is visible, right? A rocket is to be designed. Yeah, exactly. So we can use the relation for thrust as well. So the thrust is equal to m dot v at the exit, right? And the thrust is given for this problem, that is 5 kilonewtons, 5 meganewton. And m dot is required, and v exit we have calculated. Okay, so um, right, m dot with this you will get 2515.803 kgs per second. Okay, then coming on to the third problem, that is the throat diameter. So how will you calculate the throat diameter now? So this is the CD nozzle, and you know what is the mass flow rate at the exit, and which will be equal to the mass flow rate at the throat, right? So can you tell how to calculate the throat diameter? Okay. So what we can do here is we can, since we know the nozzle is choked, okay. So so the mass flow rate for the choking condition uh, is P naught AT, or we can do it in this way. Uh, P star, okay, rho star. Here will be rho star, A star. Okay, star is the quantity which I'm referring to this throat. Okay, into V star. Okay. So what is rho star? Rho star can be written as from the ideal gas relation P star by R T star into A star into V star. Okay, V star also can be written as Mach number at the throat into gamma R T star. It is correct now. Uh, till this point, it is clear now. We are just using this continuity equation, and we want to find what is a area with this relation. And from if we once we get the area, we can calculate what is the diameter. Correct? I hope this is clear to all. Uh, okay. So let us move ahead. So the mass flow rate, we know 2515.803. So so now how to calculate this P star? Any idea? How to calculate this P star? If you know the P naught and T naught, and what will be the Mach number at the throat? Mach number will be th 1, right? Pascals. Okay. So now to calculate P star, what we can use the isentropic relation, that is P naught P star by P. Okay. This is P naught by P star is equal to 1 plus gamma minus 1 by 2 m square gamma by gamma minus 1. Correct? This relation, I hope everyone knows, right? So we are calculating the condition at the throat. So MT will be 1. P star you can calculate with this as, okay, if you calculate this, okay, with this, you will get P naught by P, gamma minus 1 by 2, gamma by gamma minus 1. You will get this relation as 1.8929 P naught by P star. Okay, so P star with this you can calculate. Uh, okay, so okay, let us keep it in this way only. Uh, then similarly we can calculate what is T naught by T star, uh, which will be 1 plus gamma minus 1 by 2 and T square. This is 1 point. If you calculate, you will get 1.2 for gamma 1.4. Okay, so similarly, uh, velocity will be equal to gamma r t star. This will be okay. Now what you do is you T naught you know you'll get T star as uh, okay. Mm, mm, 1 minute. So this is okay. Let us keep it in this way only. So if you calculate V star is equal to gamma T star, this is 1.4 287 into 2800 by 1.2. So you will get this as um, 968.2630. Okay. So this is meters per second. This is the velocity of sound at the throat. Okay. So okay. So m dot at the throat is P star R T star into A into V star. We can multiply uh, and divide by P naught, right? So you will get P naught by T naught we can divide, um, and also we can multiply P star by P naught and T naught by T star. Or directly, what you can do is you can calculate the using this relation, the choked area relation. You can use this relation directly and calculate what is AT. Okay, so this is the other way that I'm using. So P naught RT star into V star. Okay. Since now this quantity we know, right? This is 1.2 uh, and divided by 1.8929 into 7 into 10 to the power 6 by 2800 into A star by 287 into 968.2630 2515.803. So the A star you will get as 0.4705, which is equal to with this you can calculate what is the diameter. You get as 77.40 centimeters. Okay, so I hope you all guys are there with me. Just correct, no? Okay. So the throat diameter is now known. Can you calculate what is the exit area? So any idea how to calculate the exit area? Okay. To calculate the exit area, again what we know is the mass flow rate. Okay. Also we know what is the P exit. Okay. So so mass flow rate is equal to rho exit A exit into V exit, right? Now, uh, now P exit, so rho exit can be written as P exit by R T exit. Okay, so this A exit, uh, okay, or otherwise, right? Okay, this you can do, yeah. So A exit and V exit can be written as, uh, give me a minute. So, so okay, so this is known, no? Okay. Let us okay, this is correct. P exit, R T exit, A exit, and V exit. Okay, so with this, what we do is P exit is 101325, T exit is 2800, and right? Or otherwise, what we can do here is A star A, A uh, okay. The other way which I'm thinking about is uh, okay. Okay, let us also try. We can use this relation. Uh, So what we can do here is uh, we know P naught, we know P exit, which is 1 plus gamma minus 1 by 2 m square gamma by gamma minus 1. So P naught is 7 into 10 to the power 6, and this is 101,325. 1 plus 0.4 by 2 m square. We do not know. We do not know what is Mach number at the exit, right? Uh, 0.4, 1.4. So with this, you can calculate what is Mach number exit, which once you calculate, you will get as 3.43059. Okay, you can calculate what is Mach number at the exit. Once you know the Mach number at the exit, so probably what you can do is you can calculate using A by A star, which is uh, which is this relation. Uh, okay. So this is gamma plus 1 by 2. So this is 1 by 2 mm, to the power. So, so this is gamma plus 1 by 2 to the power. Okay. Okay. So you have this relation. So A by A star is, we calculate this as A by A star is 1 by m, 2 by gamma plus 1, 1 plus gamma minus 1 by 2 m square to the power gamma plus 1 divided by 2 gamma minus 1, right? So if you substitute this Mach number, you will get A by A star, which is uh, which is equal to okay. Can somebody calculate and tell me this value? So probably you'll get this value as uh, so so with this you will get 1.34. Can somebody please calculate and tell me what is the value of this? Uh, so this is, if you calculate this, you will get 1.3459. So you'll get this thing earlier 6.3634 A by A star. Now A star we have calculated earlier, and yeah, that came out to be 0.47. So if you calculate A with this area at the exit, you will get as 2.9934 meter square. So the diameter at the exit you can calculate. So So the diameter you will get as 1.9522 meters. Okay. So next thing is we have to calculate what is thrust at 30 kilometers of altitude. So any idea how to calculate the thrust at 30 kilometers of altitude? So what things will change in this? It is also given 30 kilometers of altitude for a same nozzle dimensions. Any idea what parameters will change? Okay, so probably what will happen is um, the for the thrust equation, you will have m dot v plus p exit minus pa into a exit. So you will have an additional term for this part also. So for 30 kilometers of altitude, uh, you will have so so okay. So we will have this will remain same 2515.803 uh, then 1987.4367 uh, plus for 30 kilometers of altitude. Uh, so we have the p exit as 1.1855 into 10 to the power 3 pascals. Okay. And since our nozzle was designed for the sea level condition, so it will be 101,325 pascals. So this is minus 1.1855. Okay, this is plus on that. So this is P. This is okay. This is 101,325 minus 1.1855 into 10 to the power 3 into the area exit. Area exit is 2.9934. So if you calculate, you will get the thrust as 5.299975 meganewtons. Okay. So right. So with this, you can calculate what is the thrust at the nozzle exit. So okay. So uh, okay. So let us move to the other problem where I have taken the I have taken a problem from Ramamurthy sir's book. So it is as follows: in a rocket propellant, in a rocket propellant, high temperature and high pressure gases are at 3000 Kelvin, and the pressure is given. Also, the characteristics velocity is given. So the characteristics velocity is given, C star is given, and the thrust coefficient is given. Now it is asked what is the specific impulse of the rocket. Okay, this is by rocket propulsion by Professor Ramamurthy. So this this is rocket propulsion by Professor Ramamurthy. Okay, so and what must be the throat diameter of the nozzle? Okay, so these two things are asked. So any idea how we'll approach this problem? So how will you calculate what is the ISP for the rocket? Okay, right, right. So what is the formula which you will use? Right. So this is just CF into C star. So uh, so if it is just 2000 multiplied by 1.5. Yeah, you're right. So next thing is you have to calculate what is the throw diameter for 5 kilonewtons of thrust. So how will you calculate this? Any idea? Throw diameter. So okay, for throw diameter, the thrust is equal to C coefficient uh, coefficient of thrust multiplied by chamber pressure multiplied by the throw diameter. Okay, you can use this relation to calculate what is the throw diameter of the nozzle. Okay, so coming on to the second problem. So a rocket, no I hope you can see the problem, right? Is it visible? Okay, okay. So a rocket is designed to produce 5 kilonewtons of thrust at sea level. The pressure in the combustion chamber is 7 megapascal and the temperature is this. I think this is just as similar to what we have done, right? So the specific impulse is asked, mass flow rate, and the throw diameter is asked. Okay. So this is something what we have done right now. So okay, let us see the third problem. For a idle rocket, C star is given, a rocket nozzle diameter is given, and the thrust coefficient is given. Also, the mass flow rate is given. Can you calculate the chamber pressure? Okay, so let us see what all things are given, and we'll try to solve this problem. Okay, so okay, so basically, C star is given for a rocket. Um, okay, then we have throat diameter and thrust coefficient. Throat diameter 18 centimeter and thrust coefficient is 1.38. Okay. Now the and mass flow rate is given. Mass flow rate is given. This is equal to 40 kgs per second. Now it is asked what is the chamber pressure. So how will you approach this problem? Any idea? Next is thrust specific impulse. Huh. Please go ahead. So probably what we can do is we can use choke mass flow rate equation, that is P naught AT under root of T naught gamma by R. Um, yeah. So the equation was? Mm, yeah. So this is gamma 2 by gamma plus 1. So this is 2 by gamma plus 1, gamma plus 1 by 2 gamma minus 1, right? So this is the choke mass flow rate equation. Uh, okay, so let us see whether we can solve using this equation. So P naught is unknown. This is unknown. Uh, Area of the throat. Yes, we can calculate using the diameter, which is pi into 0.18 square by 4. Then the other thing is T naught. T naught is not given. Or the other thing is we have C star, right? C star is M naught by P naught AT, right? So if this is given, we can calculate what is the throat area. So hello, hello. Okay. So we have another relation, that is the C star. C star is just uh, mm, uh, P naught AT by M dot, right? So this is P naught AT by M dot. This is okay. So P naught for a we do not know. Chamber throat diameter we know. M dot is 640 and C star is 1500. P naught we do not know. This is 0 point. Okay. So if you calculate this thing, uh, so you will get this thing as, so you will get 3.8976 megapascals. Okay. So let us calculate what is thrust for this equation. Okay. Let us calculate what is thrust. So thrust is equal to C star CF uh, into M dot, right? Am I correct? Am I correct? C star is thrust is M dot C star into CF. So M dot is 40, C star is 1500, and this is 1.38. So if you multiply these three relations, so you will get 82.8 kilonewtons of thrust. Okay. So coming on to the other third part, uh, Pratik, right? So yes, there is a good book by uh, hello. Yeah. Satish, you want to ask something? Hello. Okay. So Pratik, right? You want to ask a book about this compressible flow? Okay. So yeah, there are few books. Maybe I'll write. Uh, okay. So there is one book by there is a book known as Gas Dynamics by John and Keith. So this is John and Keith. Then there is Modern Compressible Flows by uh, uh, J.D. Anderson. Then you have there is a book by I don't know the correct name, by Gas Dynamics by Shapiro. Okay, Shapiro. Then other is, if you want to go for a Indian author, then that is, I don't know the name of the book. I think Compressible Flows. Compressible Flows uh, by S.M. Yaha. Yeah, I guess. Yeah. Yeah, I think these books would be sufficient, I guess, for you to learn about this compressible flows. Okay. So, Okay, yeah. So coming on to the other part, the the specific impulse. So the specific impulse is C star CF. This is 1500, 1.38. Okay, so this is 2070 I mean, meters per second. Uh, Meters per second. Yeah. So, okay. So, any other doubt you guys have? Maybe if you want, we can have another problem of such kind. Any other doubt? Or okay. Can you guys tell me one thing? Do you find solving problems is better, or you want that concepts also to be cleared, or directly we can from next time we can jump onto the problems. Okay. 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 So, okay, you want we can have another problem of such kind, huh? So, so probably maybe I'll try to take up some. Okay, so optimum interest. Okay, let us look at this problem number 7. That is, determine the diameter at the throat and the exit of the nozzle of an ideal nozzle. Okay, of an ideal nozzle, design nozzle. So for optimum thrust at a altitude of 25 kilometers. Okay. Uh, the thrust generated by rocket at 25 kilometers is 5 kilonewtons. The chamber pressure is this 2 megapascals, and hot gases are 2800 Kelvin. The ambient pressure is 2610 pascals. Mean molecular weight is given, uh, and gamma is given. Okay, so we have to calculate what is the diameter of the throat and the exit. Okay, so maybe I'll write it down here. So question number 7. So what we are asked here is to calculate the throat diameter and the exit diameter meter. Uh, okay, so the thrust is given 5 kilonewtons uh, at an altitude where the pressure exit is 2610 pascals, and T naught is 2880 Kelvin. P naught is 2.7 megapascals. I think I have not missed anything. Okay, nothing else. 23.4. Okay, R is given as 23.4 kg per kilomole. Okay, kilojoule per kg. Kilojoule per kg. Kelvin. Not R is not given. Okay, it's the molecular weight is given. 23.4 kg per kilomole. Gamma is given as 1.3. So, any idea how we are going to tackle this problem? Any idea? So, I think this is similar to what we have done in the first problem. So, to do that, what we have to do is, since we know the thrust, uh, okay, or what we can do here is we can calculate what is the mass flow rate using the thrust. Okay, thrust is m dot v exit. So v exit you can calculate using this relation 2 gamma Ru by gamma minus 1 into molecular weight into T naught 1 minus P exit by P naught gamma minus 1 by gamma. So can somebody calculate this and let me know what is the value? Can somebody do this? With this, what I am getting here is 2748.0268 meters per second. Okay, thrust is given as 5 kilonewtons. Uh, V exit m dot. So m dot you can calculate with this as 1.8194 kgs per second. Okay, so you have m dot. So now what you can do is you can use P naught, A throat, gamma. Okay, that should be RT naught, gamma 2 by gamma plus 1, gamma plus 1 by 2, gamma minus 1. Okay, so you have 1.8194. P naught is given 2.07 10 to the power 6. R, okay, R is Ru by molecular weight. So this is 8314 divided by 23.4. So you will get this thing as 355.299 into 2880 1.4 uh, with this 2 by 2.3 2.3 2.3 uh, divided by 2.3 divided by 0.6. So and there will be a 8 throat. Okay, so if you calculate this thing, mm, so area of the throat you can calculate as 8.39 into 10 to the power minus 4 meter square. Okay, to calculate the the exit diameter, what we can do here is, since it is given that the nozzle is ideal is working in an optimum condition, so we can use a isentropic relation, that is P exit by P naught is equal to 1 plus gamma minus 1 by 2 m square gamma gamma by gamma minus 1. Okay, so 1 plus 0.15 into m square 1.3 by 0.3. So P exit we know 2610, P naught we know 2.07 10 to the power 6. So with this you can calculate. Okay, 1 minute. It should be other way around. This is P naught P exit 2.07 10 to the power 6 into 2610. 2.07 10 to the power 6 where 2610. Uh, yeah. So to the power 0.3 divided by 1.3. So with this Mach number you will get as 4.944. Okay. So now what you can do is you can use this relation A by A star is equal to 1 by M. So right. So you can use this relation by M. 2 by gamma plus 1, 1 plus gamma minus 1 by 2, M square, gamma plus 1 by 2 times of gamma minus 1. Okay. So from here you can calculate what is the uh, exit area, right? So this is okay 1 plus 0.15 into square uh, into 2 divided by 2.3 power 2.3 divided by 0.6. Okay, this is some 43.44 A by A star. So A star was 8.39 10 to the power minus 4. So this is area of the exit is 0.03645 meter square. Okay. So with this you can calculate your uh, the exit area and the throat area. Okay, so probably you'll find problems like this. If you have any other doubt, please let me know. So any doubt, whatever we have done so far. Uh, so PDF, okay, I don't think it is available anywhere. But yeah, you can always purchase this book on Amazon. I think it is available on Amazon, and it is not as this much costly. It is around 300 400 rupees. So uh, this Ramamurthy, Professor Ramamurthy's book. So so the book name is I think Rocket Propulsion by Ramamurthy, Professor Ramamurthy. Maybe I'm having that book. So, uh, yeah. So uh, okay, no doubts, right? Anything else? So yeah. So the book name is Rocket Propulsion by K. Ramamurthy, and it is by Trinity Press. I'll mention this thing in the chat box. Okay. Okay. Uh, Murthy, uh, Trinity Press. Okay. So anything else? If you have any doubt, please let me know. So I'll also share this slides with you or this PDF with you if you can go back and have a look. Okay. So right. So with this, maybe I'll end the session. Uh, okay. Uh, I think it will be the fourth week, probably. Yes. Okay. So, yeah. Okay. So, thank you all. Okay. So, if you have any doubt, you can let me know, or otherwise, uh, okay. So, anyways, yeah, thank you all.